In the deepest laboratories on Earth, scientists have uncovered something that breaks every rule of reality we thought we understood. Particles that seem to remember the future, information flowing backward through time, objects existing in multiple places at once until someone dares to look. These aren't science fiction fantasies. They're quantum paradoxes that have left brilliant minds questioning whether reality itself is nothing more than an illusion. We're about to walk through 26 of the most disturbing puzzles in all of physics, where consciousness might be creating the universe, where your choices can rewrite history, and where the simple act of looking tears holes in the fabric of logic itself. A single photon of light moves toward two narrow slits cut into a metal barrier. Simple enough, right? You'd expect the photon to pass through one slit or the other, like a marble rolling through a doorway. But quantum mechanics has no patience for such reasonable thinking. When scientists fire individual photons at those slits, something impossible happens. Each photon somehow passes through both slits at the same time, producing an interference pattern on the screen behind it, the unmistakable signature of waves colliding with themselves. This makes no sense. A particle cannot occupy two places simultaneously. Yet the evidence is right there, painted in light on the detector. Bright and dark bands that can only appear when waves meet and either reinforce or cancel each other out. One photon, both openings, at once. But here's where it gets even stranger. The moment scientists try to watch which slit the photon actually uses, the interference pattern vanishes. The photon suddenly behaves like an ordinary particle, choosing one path and leaving a single mark. The act of observation alone destroys the effect. Scientists have tried every trick imaginable to fool these particles. They've used detectors that barely interact with the photons. They've made measurements so gentle that the photon should hardly register being watched. Nothing works. The universe seems to possess some all-seeing awareness that knows precisely when we're trying to peek behind the curtain of reality. The implications bleed far beyond physics into philosophy. If particles change their behavior based on whether they're being observed, what does that mean for reality itself? Were the photons always passing through both slits, simply waiting for us to force them to choose? Or do they genuinely exist in multiple states until measurement collapses them into a single outcome? Physicists have spent decades wrestling with this. They've proposed hidden variables, parallel universes, and conscious observers creating reality through the act of measurement. None of these explanations feels complete. The double-slit experiment remains just as baffling today as it was a century ago. Even more unsettling is what this implies about existence at large. If fundamental particles have no definite properties until observed, what about the atoms in your body? What about the chair you're sitting on? What about the world around you when nobody's looking? The photon hits the screen and leaves its mark, in a pattern that defies all explanation. Scientists record the data, knowing they've witnessed something that challenges the very foundation of reality. And this is only the beginning. Because what happens when we try to observe these particles becomes even more disturbing when we realize that light itself can choose its own identity based on decisions we haven't even made yet. Light has been playing a cosmic game of hide-and-seek with physicists for over 3 centuries. Isaac Newton believed light consisted of tiny particles racing through space like microscopic bullets, which explained why light travels in straight lines and casts sharp shadows. Then scientists discovered that light could bend around corners and produce interference patterns, behaviors that only waves could generate. For 200 years, physicists argued about light's true nature, unable to accept that it might be both things at once. The quantum revolution shattered that debate by revealing something far more disturbing. Light doesn't simply behave like a wave or a particle. It literally becomes whatever the experiment is designed to detect. Set up an experiment to catch particles, and light arrives as discrete packets of energy called photons. Design an experiment to measure waves, and light transforms into rippling electromagnetic fields. But here's where reality starts to break down completely. Light makes this choice based on what you're planning to measure, even before the measurement happens. Scientists can prepare light in one configuration, then switch their detection method at the last possible moment. Somehow, light already knows what's coming and adjusts accordingly. Imagine a chameleon that changes color not just to match its current surroundings, but to match surroundings it hasn't even seen yet. Except this chameleon is every photon in the universe, constantly shape-shifting based on future observations that may never actually occur. The mechanism behind this transformation remains completely mysterious. There's no communication between the light and the detector. No signal travels from the measuring device to the photon. Yet the correlation is perfect. Light always arrives in exactly the right form for whatever experiment awaits it. This phenomenon extends beyond laboratory tricks. Every interaction between light and matter involves this quantum shape-shifting. When you see a red rose, photons are deciding whether to behave as waves or particles based on how your eye's receptors are structured. The color red exists because light chose to interact as discrete energy packets that match your visual system's detection method. Scientists have tried to catch light mid-transformation, to witness it switching between wave and particle. They've built detectors that can change their measurement type faster than light can travel between them. They've used quantum measurements that barely disturb the photons. Every attempt fails. Light seems to exist in a quantum superposition of possibilities until the very moment measurement forces it to choose. The mathematical description of this duality works with stunning precision. Physicists can predict exactly how light will behave in any given experiment. But the underlying mechanism, how a photon knows what type of measurement is coming, remains as mysterious as consciousness itself. This isn't just academic philosophy. Technologies like lasers, LEDs, and solar panels all depend on controlling light's wave-particle nature. We've built our modern world on a phenomenon we don't understand, harnessing a quantum mystery that challenges the very concept of objective reality. But light's identity crisis becomes even more disturbing when we discover that particles can make decisions about their past behavior based on measurements that haven't happened yet. Deep in a physics laboratory, a photon begins a journey that will challenge everything we understand about cause and effect. The setup looks innocent enough. Scientists split a single photon into two entangled particles, quantum twins that remain mysteriously connected regardless of distance. One twin travels toward a screen that will record whether it behaved as a wave or a particle. The other heads toward a distant detector where researchers can choose to either preserve or destroy information about the photon's path. Here's where time itself starts to break down. The first photon hits the screen and leaves its mark before the scientists make any decision about its twin. By every rule of common sense, the pattern should be fixed, written in permanent ink. The photon either interfered with itself like a wave or arrived like a particle. Case closed. But quantum mechanics operates by different rules. Hours, days, or even years later, when researchers finally examine the distant twin, their choice retroactively determines what the first photon did in the past. If they preserve the path information, the original photon reveals it behaved like a particle all along. If they erase that information, an interference pattern appears, proof it acted as a wave. Think of it like developing a photograph where the picture changes based on decisions you make long after taking the shot. The image on the film somehow reaches backward through time to adjust itself according to your future choices about how to process it. Scientists have stretched this effect across enormous distances, sending photons on journeys spanning hundreds of miles, with detection choices made on different continents. The correlation remains perfect. A decision made in Tokyo instantly affects a photon that arrived in New York hours earlier. The most unsettling version involves astronomical distances. Imagine a photon from a distant quasar traveling billions of years through space before reaching Earth. Scientists can split this ancient light and delay the measurement choice until long after the photon has already been detected. According to quantum eraser experiments, our decision today about how to measure this photon can retroactively determine whether it behaved as a wave or particle during its billion-year journey across the cosmos. This isn't theoretical speculation. Multiple laboratories have performed these experiments with consistent results. The future genuinely appears to influence the past at the quantum level. Information flows backward through time as easily as it flows forward. The implications stagger the mind. If quantum decisions can reach across years or centuries, what prevents them from reaching across millennia? Could our measurements today be determining the quantum behavior of particles that existed before Earth formed? Are we inadvertently reaching back to influence the quantum processes that shaped the early universe? Some physicists argue that quantum eraser experiments don't truly demonstrate reverse causation, just the strange non-local correlations that Einstein called spooky action at a distance. But the mathematics suggests something far more radical. The future may be reaching into the past, editing the quantum story of reality based on observations that haven't happened yet. John Wheeler, one of the greatest minds in physics, proposed an experiment so disturbing that it took decades for technology to catch up with his vision. Picture a single photon traveling toward a beam splitter, a device that offers the photon two possible paths. Under normal circumstances, the photon would have to commit to one route or the other before continuing its journey. But Wheeler imagined something more sinister. What if scientists could delay their choice about how to detect the photon until after it had already passed the beam splitter? The setup sounds like science fiction. The photon approaches the crossroads and must somehow decide whether to take one path like a particle or explore both simultaneously like a wave. But the scientists don't configure their detection equipment until the photon is already committed to its journey through the apparatus. When researchers finally performed Wheeler's delayed choice experiment, the results were exactly as terrifying as he predicted. The photon's behavior depended entirely on choices made after it had supposedly already traveled through the system. Configure the detector to look for a particle, and the photon retroactively becomes a particle that chose just one path. Set up the detector for wave behavior, and evidence emerges that the photon explored both routes at the same time. Think about watching a movie where the ending changes every time you decide how you want it to finish, except the decision happens after the movie is already over. And somehow the entire plot rearranges itself to match your future choice. The timescales involved make this even more mind-bending. Scientists can delay their measurement choice by minutes, hours, or theoretically any amount of time. The photon waits in quantum limbo, neither particle nor wave, until a decision retroactively determines its entire history through the apparatus. Wheeler extended this concept to cosmic proportions. Consider light from a distant galaxy passing around a massive star on its way to Earth. This gravitational lensing creates two possible paths for the photon, just like a beam splitter in the laboratory. According to delayed choice logic, we could theoretically set up an experiment where our measurement today determines whether that photon took one path or both during its million-year journey through space. This suggests that consciousness might be reaching backward through time to edit the quantum history of the universe. Every observation we make could be collapsing wave functions that existed long before Earth formed. we might be inadvertently determining whether photons from the cosmic microwave background, the afterglow of the Big Bang, behaved as particles or waves 13 billion years ago. The mathematical formalism handles these paradoxes with elegant precision. Quantum mechanics predicts exactly what will happen in delayed choice experiments. But the underlying reality defies comprehension. How does a photon know what measurement is coming? How does information flow backward through time without violating causality? Each successful delayed choice experiment adds another crack to our understanding of temporal order. In quantum mechanics, the act of observation doesn't just change what you see. It literally creates what exists. Most people think of observation as a passive process, like watching a movie without affecting the plot. You open your eyes, light enters, your brain processes information about the world around you. But quantum physics reveals something far more disturbing. At the microscopic level, the very act of looking brings reality into existence. Consider an electron orbiting an atomic nucleus. Before measurement, that electron has no definite position or velocity. It exists as a ghostly cloud of probabilities, simultaneously occupying multiple locations and states. The mathematics describes this perfectly. A wave function encoding every possible property the electron might have. But the moment you try to detect where the electron actually is, something catastrophic happens. The entire probability cloud collapses into a single point. All those potential positions vanish instantly, leaving behind just one definite outcome. The electron suddenly becomes real in the classical sense, but at the cost of erasing every other possibility that existed a moment before. This isn't simply a measurement problem where clumsy instruments disturb delicate particles. Scientists have developed quantum measurements so gentle they barely touch the systems they're observing. The collapse still happens. Reality seems to crystallize from pure possibility the instant consciousness encounters it. Think of it like a video game that only renders graphics when you're looking in a particular direction. Behind you, the world exists as pure code, potential rather than actual. Turn around, and the processor instantly calculates what should be there, creating a believable reality that feels like it was always present. The implications reach far beyond laboratory experiments. If electrons collapse into definite states only when observed, what about the atoms in your body? Are they existing as probability clouds until some form of consciousness detects them? What qualifies as an observer capable of collapsing quantum states? Some physicists argue that observation requires conscious awareness, that human consciousness literally creates reality through the act of perception. Others propose that any interaction between quantum systems counts as observation, removing the need for a conscious witness. But neither explanation resolves the central mystery of why reality appears to need outside intervention to become definite. The Copenhagen interpretation, developed by Niels Bohr and colleagues, simply accepts quantum collapse as a fundamental feature of reality. They argue that asking what happens before measurement is meaningless, like asking about the sound of one hand clapping. Reality exists only in the interaction between quantum systems and classical measuring devices. But this raises even more disturbing questions. If reality doesn't exist until observed, what was the universe doing for the billions of years before conscious observers evolved? Were galaxies, stars, and planets existing as vast probability clouds, waiting for someone to look at them? The measurement process transforms infinite potential into singular actuality in ways that violate every intuition about how existence should work. Each observation creates reality while simultaneously destroying all the other realities that could have been. Eugene Wigner created a thought experiment that splits reality in two, leaving physicists questioning whether truth itself can be objective. Imagine your friend locked inside a completely isolated laboratory, performing a quantum measurement on a spinning particle. From your friend's perspective, the measurement has a definite outcome. The particle is spinning either clockwise or counterclockwise. Your friend writes down the result and believes the quantum mystery is solved. But you're standing outside the laboratory, and quantum mechanics tells a different story. Since you can't see inside, you must treat the entire system, your friend, the particle, and the measurement apparatus, as a single quantum entity. From your perspective, everything inside exists in superposition. Your friend is simultaneously observing a clockwise spinning particle and a counterclockwise spinning particle existing in both realities at once. Here's where logic breaks completely. Your friend experienced one definite outcome, but you're describing them as being in two contradictory states simultaneously. Both of you are using quantum mechanics correctly, yet you're reaching opposite conclusions about the same event. Either the particle collapsed when your friend measured it, or it remained in superposition until you opened the laboratory door. This isn't just philosophical hair-splitting. If your friend truly exists in superposition from your perspective, they would be experiencing both measurement outcomes simultaneously, an impossible mental state that defies everything we understand about awareness. Think of it like two security cameras watching the same crime, but recording completely different events. One shows the criminal stealing a car. The other shows the same person at the same moment, helping an elderly woman cross the street. Both recordings are accurate according to their own perspective. But they can't both be true in any sensible version of reality. Modern experiments have pushed Wigner's paradox beyond thought experiments. Scientists have created scenarios where multiple observers make measurements on entangled quantum systems, leading to contradictory but equally valid descriptions of the same physical events. Each observer's quantum calculations are mathematically correct, yet their conclusions about reality are incompatible. Some physicists argue that consciousness plays a special role, that only conscious observers can collapse quantum states, while unconscious measuring devices cannot. But this requires consciousness to possess mysterious powers that transcend known physics. Others propose that quantum mechanics simply doesn't apply to large objects like human beings, that once systems become complex enough, they automatically behave classically. Yet, no one can explain where that boundary lies or why atoms follow quantum rules while people follow classical ones. The many worlds interpretation offers a different resolution. Both you and your friend are correct because you exist in separate branches of reality. Your friend experiences one definite outcome in their branch while remaining in superposition from the perspective of yours. But this solution multiplies the problem. If every quantum measurement splits reality into parallel worlds, then consciousness itself might be branching continuously into countless versions, each unaware of the others. At the heart of quantum mechanics lurks a problem so fundamental that it threatens to unravel our entire understanding of reality. The equations of quantum physics work with supernatural precision. They predict the behavior of atoms, molecules, and subatomic particles with accuracy that exceeds nearly every other scientific theory. Quantum mechanics has given us computers, lasers, magnetic resonance imaging, and countless other technologies. Yet despite this practical success, the theory contains a logical contradiction that has stumped physicists for a century. Quantum mechanics describes particles as wave functions, mathematical expressions encoding all possible properties a system might have. These wave functions evolve smoothly and predictably according to the Schrödinger equation, growing and shrinking and interfering with each other in ways that can be calculated exactly. But then something catastrophic happens during measurement. The smooth, deterministic evolution suddenly stops. The wave function undergoes what physicists call collapse, an instantaneous transformation from multiple possibilities into a single definite outcome. This collapse violates the very equations that make quantum mechanics work in the first place. Think of it like a finely tuned orchestra playing a complex symphony. Every instrument follows the written score perfectly, creating beautiful harmonies that unfold exactly as the composer intended. Then, without warning, all the musicians stop playing their assigned parts and randomly choose new notes. The music becomes chaos, but somehow the audience hears only one coherent melody. The measurement problem asks when, where, and how this collapse happens. If wave functions follow deterministic equations, what causes them to suddenly become random? If quantum systems exist in superposition until measured, what qualifies as a measurement? Why does the microscopic quantum world transition into the definite classical world we experience? Scientists have proposed dozens of solutions. Some argue that consciousness causes collapse, that human awareness literally creates reality by observing it. Others suggest that large systems automatically become classical through interactions with their environment, a process called decoherence. Many worlds. Interpretation sidesteps the collapse entirely by allowing all possibilities to occur simultaneously in parallel branches, preserving the elegance of quantum mechanics at the cost of infinite parallel universes. The most disturbing possibility is that measurement doesn't solve the quantum puzzle at all. It just pushes the mystery one level deeper. Every detector designed to observe a quantum system is itself made of atoms that should follow quantum rules. When a particle detector clicks, indicating it found a particle, what causes the detector's own wave function to collapse into the clicked state? This leads to an infinite regress. To explain how one quantum system becomes definite, you need another quantum system to observe it. But then you need a third to observe the second, and a fourth to observe the third, extending the chain forever with no ultimate foundation. The measurement remains suspended between quantum possibility and classical reality, waiting for a resolution that may not exist. Quantum superposition sounds harmless in textbooks, but its true implications are the stuff of nightmares about the nature of existence itself. The standard explanation makes superposition seem almost mundane. A quantum particle can exist in multiple states simultaneously until measurement forces it to choose. An electron spins both clockwise and counterclockwise. A photon travels through multiple paths at once. These descriptions capture the mathematics, but they fail to convey the existential horror of what superposition actually means. Consider what it would feel like to be in superposition, not a particle, but you, right now. Quantum mechanics suggests that the atoms in your brain exist in countless overlapping states. Your neurons are firing and not firing simultaneously. Every synapse is both active and inactive until some form of measurement collapses them into definite configurations. If consciousness emerges from brain activity, and brain activity is quantum mechanical, then your thoughts might exist in superposition too. You could be simultaneously happy and sad, remembering and forgetting, making every possible decision about what to do next. With only the act of self-observation collapsing your mental state into the single stream of consciousness you experience. Think of it like living inside a house of mirrors, where every reflection shows a different version of yourself making different choices. You see only one reflection at a time. But quantum mechanics suggests all the other versions are equally real until the moment you look in the mirror. The implications extend to the nature of reality itself. If superposition applies to large-scale objects, and nothing in quantum theory prevents this, then entire cities might exist in multiple configurations simultaneously. Buildings could be both constructed and demolished. People could be both alive and dead. The entire planet could exist in a superposition of every possible state it could occupy. This isn't just philosophical speculation. Scientists have successfully created superposition states in increasingly large objects. They've put molecules containing hundreds of atoms into superposition. They've made tiny mechanical devices that vibrate and don't vibrate at the same time. Each experiment pushes the boundary between quantum weirdness and everyday reality a little further. Some researchers are working toward placing living organisms in superposition, wanting to know whether bacteria, viruses, or even larger creatures can exist in multiple states simultaneously. But superposition creates a paradox about identity. If you exist in multiple states simultaneously, which one is really you? Are all the superposed versions equally valid? When superposition collapses, do the other versions simply cease to exist? Or do they continue living in parallel realities you can never access? The mathematical formalism handles superposition with elegant precision. Physicists can calculate exactly how multiple states interfere with each other, predicting experimental outcomes with extraordinary accuracy. But the lived experience of superposition, what it would feel like from the inside, remains completely mysterious. Every quantum measurement destroys vast ranges of possibility, collapsing infinite potential into singular actuality, while leaving us to wonder what happened to all the other versions of reality. Erwin Schrödinger created his famous cat thought experiment to show how ridiculous quantum mechanics becomes when applied to everyday objects. But modern physics suggests the joke is on us. The original setup seems straightforward. A cat sits in a box with a Geiger counter connected to a hammer poised above a flask of poison. When the Geiger counter detects radiation from a decaying atom, a purely quantum event, the hammer smashes the flask and kills the cat, until someone opens the box to check. Quantum mechanics insists the atom exists in superposition, both decayed and undecayed. Therefore, the cat must be both alive and dead simultaneously. Schrödinger intended this as a proof by absurdity, evidence that quantum theory couldn't possibly apply to macroscopic objects. Surely a real cat could never exist in such a contradictory state. But subsequent developments in quantum physics have made the cat's predicament far more plausible and infinitely more terrifying. Scientists now understand there's no fundamental barrier preventing large objects from entering superposition. The boundary between quantum and classical behavior isn't written into the laws of physics. It emerges from practical limitations about maintaining quantum coherence in complex systems. Under the right conditions, even macroscopic objects can exhibit quantum behavior. This means your neighbor might literally be both alive and dead right now, existing in quantum superposition until you knock on their door. Every person you haven't seen recently exists in a ghostly state of overlapping possibilities, sleeping or awake, healthy or sick, happy or miserable, all simultaneously real until observation collapses them into a single definite state. The implications cascade through every aspect of existence. Your coffee mug sits on the table in superposition, simultaneously full and empty, hot and cold, even broken and intact. The traffic light down the street displays all colors at once until you look at it. The money in your bank account exists in superposition of every possible amount until you check your balance. Think of reality as a vast probability cloud where everything exists in every possible state until consciousness touches it. Your home is simultaneously clean and messy. Your phone battery is both charged and dead. Your refrigerator is stocked and empty. The act of living becomes a series of quantum measurements that collapse infinite possibilities into the single timeline you experience. But here's the truly disturbing part. If consciousness causes quantum collapse, then unconscious people might remain in superposition indefinitely. Everyone who's sleeping, in a coma, or simply not paying attention could be stuck in quantum limbo, neither fully alive nor dead, but existing in all possible states simultaneously. Some interpretations of quantum mechanics suggest that the entire universe exists in superposition, except for the tiny bubble of collapsed reality surrounding conscious observers. We walk through a world of ghostly possibilities, our awareness carving out definite experiences from an ocean of quantum potential. The cat remains trapped in its box, simultaneously alive and dead, waiting for an observer whose measurement will eliminate half the quantum possibilities to create just one definite reality. Albert Einstein called it spooky action at a distance. And after decades of experimental verification, quantum entanglement has proven to be far spookier than even Einstein imagined. When two particles become entangled, they form a connection that transcends space and time. Measure the spin of one particle and you instantly know the spin of its partner, regardless of how far apart they've traveled. This isn't just correlation. It's instantaneous influence across any distance, happening faster than light could ever travel between the particles. The setup seems innocent enough. Scientists create pairs of particles with opposite properties, then send them racing in different directions. According to classical physics, each particle should have definite properties from the moment of creation. If one spins clockwise, the other must spin counterclockwise. Simple conservation of angular momentum. But quantum mechanics reveals something far more disturbing. Before measurement, neither particle has a definite spin. They exist in what physicists call an entangled superposition, a single quantum state that describes both particles simultaneously. Even when separated by millions of miles, the system remains unified, as if space itself doesn't exist at the quantum level. When you measure one particle and find it spinning clockwise, the other particle doesn't just happen to be spinning counterclockwise. It becomes counterclockwise at that exact moment. A measurement on Earth instantly affects the state of its partner orbiting Jupiter. Information appears to travel across the solar system instantaneously, violating Einstein's speed limit for the universe. Think of it like two coins that always land on opposite faces, but neither decides heads or tails until one of them hits the ground. The moment the first coin lands heads in New York, its partner automatically becomes tails in Tokyo, with no time for any signal to travel between them. Scientists have tested this spookiness across increasingly vast distances. They've entangled particles separated by hundreds of miles, confirming that the connection remains perfect regardless of how much space lies between them. They've closed every possible loophole that might explain the correlation through classical means. The universe genuinely appears to support instantaneous connections between distant objects. The implications shatter our understanding of locality, the idea that objects can only be influenced by their immediate surroundings. If entangled particles can affect each other across arbitrary distances, then the boundary between separate objects becomes meaningless. Everything in the universe might be secretly connected through invisible quantum threads. Some physicists propose that entanglement reveals the true structure of reality. Rather than separate objects interacting across space, we might live in a single unified quantum system where the appearance of separation is just an illusion created by our limited perspective. Others suggest that entanglement allows information to flow backward through time, as well as across space. that the measurement determining one particle's spin might be reaching into the past to coordinate with its partner's behavior, creating the appearance of instantaneous connection. But entanglement becomes even more mysterious when we realize it isn't limited to specially prepared laboratory particles. Every interaction between quantum systems creates entanglement, meaning the universe is constantly weaving new connections between distant objects. The entangled particles maintain their spooky connection across the cosmos, suggesting that separation itself might be the deepest illusion of all. The man who gave us relativity and unlocked the secrets of space and time spent his final decades fighting a battle against quantum mechanics, a battle he ultimately lost in the most disturbing way possible. Einstein couldn't accept that quantum mechanics painted a complete picture of reality. The idea that particles existed in undefined states until measurement seemed absurd to someone who believed in an objective universe operating independently of human observation. He was convinced that quantum theory was missing something, hidden variables that would restore determinism and eliminate the apparent randomness of quantum measurements. Together with colleagues Boris Podolsky and Nathan Rosen, Einstein devised what they thought was the perfect argument against quantum mechanics. The EPR paradox described two particles with correlated properties sent in opposite directions. If quantum mechanics was correct, measuring one particle would instantly determine the state of its distant partner, requiring information to travel faster than light. Einstein believed this violated his own theory of relativity, which established light speed as the ultimate limit for information transfer. He was certain that no influence could propagate instantaneously across space. The particles must have predetermined properties, hidden variables that explained their correlation without requiring spooky action at a distance. For decades, Einstein's argument remained a philosophical debate. Then John Bell developed a mathematical test that could distinguish between Einstein's hidden variables and true quantum entanglement. Bell's theorem showed that if hidden variables existed, they would produce correlations obeying specific statistical limits. Quantum mechanics predicted correlations that violated these limits. When scientists finally performed Bell's test, the results were devastating for Einstein's worldview. Quantum correlations exceeded Bell's limits by exactly the amount quantum mechanics predicted. The universe genuinely supports instantaneous connections between distant particles even when no information has time to travel between them. Think about this, like discovering that identical twins share not just similar genetics, but literally the same thoughts simultaneously, regardless of whether they're in the same room or on different continents. Except these quantum twins are particles that have never met, and their shared behavior extends across billions of miles. The experimental violation of Bell's inequalities proves that reality itself is non-local. The universe operates as a unified system where distant events can be intrinsically connected without any intervening cause. Space and time, the foundations of Einstein's greatest theories, become secondary to quantum correlations that transcend both. Modern experiments have closed every possible loophole that might preserve Einstein's local realism. Scientists have used random number generators to choose measurement settings, eliminating the possibility that detectors somehow coordinate their behavior. They've measured particles whose entanglement was created after the measurement choice was made, ruling out any preparation-based explanation. Each new test confirms the same unsettling conclusion. Reality is fundamentally non-local, with distant objects maintaining mysterious connections that operate faster than light. Information doesn't travel between entangled particles. Instead, they remain parts of a single quantum system that transcends ordinary space and time. Einstein's greatest fear has become modern physics' most firmly established fact. John Bell created a mathematical proof that reality as we understand it simply cannot exist, leaving physicists with a choice between nightmarish alternatives that all violate common sense. Bell's theorem addresses one of the deepest questions in physics. Do particles have definite properties before measurement? Einstein believed they must, that electrons possess real spin values and photons have actual polarizations independent of human observation. Quantum mechanics suggested otherwise, claiming that properties exist only as probabilities until measurement collapses them into definite states. The theorem works by considering correlations between measurements on entangled particle pairs. If particles have predetermined properties, these correlations must obey certain mathematical limits called Bell inequalities. But quantum mechanics predicts correlations that violate these limits, creating a stark experimental test between Einstein's classical realism and quantum strangeness. When scientists perform these tests, nature chooses quantum mechanics overwhelmingly. Bell inequalities are violated with such consistency that doubt about the results has essentially vanished. This violation forces us to abandon at least one fundamental assumption about reality. The first assumption is locality, the idea that distant objects cannot instantly influence each other. If you accept that particles have real properties before measurement, then violating Bell inequalities requires faster-than-light communication between distant measurement devices. Information must somehow travel across space instantaneously to coordinate particle behavior. Think of it like two magic 8-balls that always give opposite answers, even when shaken simultaneously on different planets. Either they're communicating faster than light, or they don't actually contain predetermined answers until the moment you shake them. The second assumption is realism, the belief that physical properties exist independently of measurement. If you accept locality as inviolable, then Bell violations prove that particles don't have definite properties until observed. The universe exists in a state of pure potential, crystallizing into concrete reality only when consciousness encounters it. The third assumption is freedom of choice, the idea that experimenters can freely choose which measurements to perform. Some physicists propose that Bell violations occur because the entire universe is predetermined, including our supposedly random choices about which experiments to conduct. In this superdeterministic scenario, the same initial conditions that create correlated particles also determine our measurement decisions, producing artificial correlations. Each escape route from Bell's theorem leads to disturbing conclusions. Faster-than-light communication destroys our understanding of causality and the structure of space-time. The absence of predetermined properties makes objective reality impossible. Superdeterminism eliminates free will entirely, making human choices as predetermined as planetary orbits. Most physicists have chosen to abandon realism rather than locality, accepting that properties don't exist before measurement. But this choice transforms physics from the study of objective reality into something more like the exploration of subjective experiences. Science becomes less about discovering what exists and more about predicting what conscious observers will perceive. Bell's theorem doesn't just challenge specific theories. It attacks the philosophical foundations of scientific materialism. The universe appears to be far stranger and more observer-dependent than anyone imagined before quantum mechanics revealed its secrets. In Alice's Wonderland, the Cheshire Cat could vanish while leaving its grin behind. But quantum mechanics has discovered something far stranger: particles that can separate from their own properties and send those properties to entirely different locations. The quantum Cheshire Cat effect emerged from careful analysis of what happens when particles travel through interferometers, devices that split particle paths and then recombine them. Scientists discovered that under precise conditions, a neutron could travel through one arm of the interferometer while its magnetic properties traveled through the other arm. This isn't just a measurement artifact or a clever interpretation. The effect has been demonstrated in multiple laboratories using neutron interferometry, where researchers can independently detect the location of the neutron particle and the location of its magnetic moment. The results consistently show spatial separation between the particle and its intrinsic properties. Imagine if your shadow could walk around independently while your body stayed in place, interacting with objects and casting shadows of its own. Except in the quantum realm, these separated properties aren't just shadows. They're measurable physical quantities that can be detected and manipulated at locations where the particle itself is entirely absent. It's even possible for multiple characteristics, spin, magnetic moment, and electric charge, to separate and travel along different routes simultaneously. The particle becomes a quantum ghost, while its properties wander the laboratory like disembodied spirits. The implications challenge our most basic understanding of what it means to be a physical object. If particles can exist independently of their properties, then what exactly is a particle? Are we studying discrete entities with measurable characteristics? Or are we observing the temporary convergence of separate phenomena that normally coincide but don't have to? Think about this like discovering that people can send their personalities, memories, and emotions to different locations while their bodies remain stationary. The person would still exist physically, but everything that makes them who they are could be somewhere else entirely, interacting with the world independently. Some researchers propose using quantum Cheshire cats for practical applications. By separating sensitive properties from the particles that carry them, scientists might be able to perform precision measurements without the interference that normally accompanies particle detection. The separated properties could probe environments too delicate for actual particles to enter. But the effect also raises profound questions about the nature of identity and existence. If properties can travel independently of particles, then the boundary between subject and attribute becomes meaningless. Objects aren't simply collections of properties. They're temporary associations between phenomena that can separate and recombine in ways classical physics never imagined. Recent theoretical work suggests that quantum Cheshire cat effects might be more fundamental than initially thought, appearing whenever quantum systems undergo partial measurements that preserve some coherence while destroying other aspects of superposition. Contextuality sounds technical, but its implications are pure nightmare fuel. The same quantum system can give completely different results for identical measurements, depending entirely on what other measurements you choose to perform alongside it. It's not that your instruments are faulty, or that particles are randomly changing their behavior. The properties themselves depend on the context of observation, in ways that violate every assumption about objective reality. Consider measuring the spin of an electron along different axes. In classical physics, the electron should have definite spin values in all directions simultaneously, like a spinning top that rotates at specific angles regardless of how you choose to measure it. But quantum particles refuse to cooperate with such reasonable expectations. Measure an electron's spin along the vertical axis first, then along the horizontal axis, and you get one pair of results. Reverse the order, horizontal first, then vertical, and the results change. Not just the second measurement, but retroactively the first as well. The act of planning to measure horizontally after measuring vertically somehow reaches backward to influence what the vertical measurement reveals. Think about this like asking someone their favorite color, but the answer depends entirely on what question you plan to ask next. Tell them you'll ask about their favorite food afterward, and they say, blue. Plan to ask about their favorite movie instead, and they retrospectively always preferred red. The person's color preference doesn't exist independently of the conversational context you create around it. Scientists have demonstrated contextuality in countless experiments using particles, photons, and atoms. They've shown that quantum systems can violate mathematical inequalities that any classical system must obey, proving that properties genuinely depend on measurement context rather than existing independently. The violation goes deeper than simple measurement order effects. In contextual quantum systems, the very question of whether a particle has specific properties becomes meaningless. Properties exist only within the framework of particular measurement contexts, disappearing entirely when you change the experimental setup. This creates a universe where objective facts cannot exist independently of the questions being asked about them. Reality becomes conversational, emerging from the interaction between quantum systems and the classical devices designed to interrogate them. The physical world transforms from a collection of objects with inherent properties into a network of potential relationships, waiting for consciousness to activate them. Some physicists argue that contextuality explains many quantum paradoxes. Wave-particle duality, quantum entanglement, and measurement collapse might all be manifestations of the same underlying phenomenon, the context-dependent nature of quantum properties. But this explanation replaces familiar mysteries with something far more unsettling. If contextuality applies beyond laboratory experiments, then every aspect of reality might depend on the observational context that surrounds it. Your own properties, your thoughts, memories, and identity might change based on how others choose to observe and interact with you. Every quantum measurement splits the universe into countless parallel realities, creating infinite copies of yourself that experience every possible outcome of every decision you never made. Hugh Everett proposed the most disturbing solution to quantum measurement problems by simply refusing to accept that wave function collapse happens at all. Instead of mysterious processes that transform quantum possibilities into classical actualities, Everett suggested that all possibilities occur simultaneously in separate branches of a continuously splitting multiverse. When you measure a quantum particle's spin, you don't force it to choose between clockwise and counterclockwise. Both outcomes happen. The universe branches into two parallel realities, one where you observe clockwise spin, another where you observe counterclockwise. Each version of you believes they witnessed the real result, unaware that countless other versions experience different outcomes in worlds they can never access. The implications cascade through every aspect of existence. Every quantum event, and quantum events occur trillions of times per second in every cubic inch of space, splits reality into multiple branches. You're constantly dividing into parallel versions that experience slightly different quantum outcomes, creating an exponentially expanding tree of alternate selves. Think about this like living in a house of mirrors where every reflection shows a different version of your life, and all the reflections are equally real. One version of you turned left instead of right at an intersection. Another never met your spouse. A third chose a different career, moved to a different city, or never existed at all because your parents never met in that particular branch. But the horror extends beyond personal choices to every quantum process in your body. The biochemical reactions powering your neurons split into parallel versions with slightly different outcomes. Your thoughts branch continuously as quantum processes in your brain explore every possible configuration. Each version of your consciousness experiences a slightly different sequence of mental states, creating an infinite spectrum of minds that all believe they are you. Some branches contain versions of you that experience miraculous luck, quantum tunneling events that cure diseases, random mutations that grant extraordinary abilities, chance encounters that lead to perfect lives. Other branches hold versions tortured by quantum bad luck, cosmic rays that cause fatal cancers, random decay events that trigger catastrophic accidents, probability fluctuations that create lives of unimaginable suffering. The mathematics suggests that most branches contain versions of you that die young due to quantum accidents. For every branch where you live to old age, countless others experience early death from quantum processes gone wrong. Yet from your perspective, you seem to survive against impossible odds, possibly because consciousness can only exist in branches where the brain remains functional. Scientists have found experimental evidence supporting the many worlds interpretation. Quantum interference effects that should disappear when systems become large sometimes persist, suggesting that parallel branches continue to influence each other in subtle ways. The multiverse might be real, with infinite versions of reality unfolding simultaneously. Every decision you make, every thought you think, every quantum event in your vicinity splits you into parallel versions that experience different outcomes. You are simultaneously living every possible life, though you can only remember one continuous thread through the infinite tapestry of existence. In a multiverse where every possible outcome occurs simultaneously, death becomes impossible from your own perspective, trapping consciousness in an eternal nightmare of increasingly improbable survival scenarios. The quantum suicide thought experiment begins with a gun connected to a quantum random number generator. Each time the trigger is pulled, a quantum measurement determines whether the gun fires or clicks empty. In a classical universe, repeated attempts would eventually result in death. But in the many worlds interpretation, every outcome happens in parallel branches. From an external observer's perspective, some versions of you die while others survive. The surviving branches become increasingly rare as the experiment continues, but they never disappear entirely. Quantum mechanics preserves at least one branch where the gun always misfires, where the quantum generator always produces the safe result, where you survive against impossible odds. But here's where the paradox becomes truly disturbing. From your own subjective experience, you can only perceive branches where your consciousness continues to exist. The versions of you that die simply stop experiencing anything, while the surviving versions continue their stream of awareness. To yourself, you would appear immortal, always finding yourself in the unlikely branch where the gun failed to fire. Think about this like playing Russian roulette with a revolver that has 1 billion chambers, only one containing a bullet. Even after pulling the trigger hundreds of times, you would always find yourself in the reality where the chamber was empty. Your survival would seem miraculous from the outside, but from your perspective, it would feel like the universe was conspiring to keep you alive. The implications extend beyond deliberate experiments to every form of mortality. In a quantum multiverse, there are always branches where cancer cells fail to spread, where heart attacks reverse themselves, where accidents miss by inches. From your subjective viewpoint, you should expect to find yourself in increasingly unlikely scenarios where death is avoided through quantum coincidences. But immortality in the quantum multiverse comes at a terrible price. The branches where you survive become increasingly bizarre. As normal aging processes require more and more improbable quantum events to reverse, you might find yourself living far beyond any natural lifespan, sustained by quantum healing processes that violate biological laws. Your body would become a patchwork of quantum miracles held together by probability fluctuations that become vanishingly rare, but never quite reach zero. Some physicists argue that quantum suicide is impossible because consciousness requires classical brain processes that don't branch the same way quantum systems do. Others suggest that the anthropic principle, the idea that we observe a universe compatible with our existence, already demonstrates quantum immortality in action. We find ourselves in the rare branch where life evolved, where Earth avoided cosmic catastrophes, where everything aligned perfectly for consciousness to emerge. The most disturbing possibility is that you're already experiencing quantum immortality. Every near miss, every lucky break, every time you survived something that should have killed you, might be evidence that you're trapped in the increasingly improbable branches of the multiverse where your consciousness persists. Each moment of continued existence pushes you deeper into branches that require ever more unlikely quantum events to sustain your survival, creating a form of immortality that resembles eternal imprisonment. At the deepest level of quantum mechanics lies a question that terrifies physicists. Does consciousness create reality? Or does reality create consciousness? And what happens if we get the answer wrong? The measurement problem in quantum mechanics refuses to go away. Wave functions evolve deterministically until something called measurement happens. Then they collapse randomly into definite states. But what qualifies as measurement remains mysteriously undefined. Does it require conscious observation? Or can unconscious processes trigger collapse? The answer might determine whether minds create the universe or emerge from it. Some interpretations place consciousness at the center of quantum reality. In this view, the universe exists as a vast superposition of possibilities until conscious observers force it to choose specific outcomes. Your awareness literally creates the reality you experience by collapsing quantum states through the act of observation. Before consciousness evolved, the universe was a ghostly realm of pure potential, waiting for minds to bring it into existence. Think about this like being the director of a movie that only gets filmed when someone is watching. Until you focus your attention on a particular scene, it exists only as a script full of possibilities. Your consciousness transforms potential storylines into actual events, creating reality through the act of perception. But this explanation raises horrifying questions. If consciousness creates reality through quantum observation, what happens to the universe when you're not paying attention? Do objects continue to exist while you sleep? Or does reality dissolve back into quantum superposition until you wake up? When you look at the stars, are you creating ancient light that traveled for billions of years? Or are you retroactively determining what was always there? The alternative is equally disturbing. If consciousness emerges from purely classical brain processes, then awareness becomes an illusion created by complex arrangements of unconscious matter. Your sense of being a unified, experiencing self would be nothing more than information processing in neural networks that only feel like consciousness from the inside. Recent experiments have tried to test consciousness-based collapse by isolating quantum systems from human awareness while monitoring them with unconscious detectors. The results remain ambiguous. Quantum states seem to collapse whether or not conscious observers are present. But the interpretation of these results depends on assumptions about what constitutes consciousness and measurement. Some physicists propose that consciousness and quantum mechanics are fundamentally incompatible. They argue that classical neural processes cannot directly observe quantum systems, eliminating any special role for awareness in determining physical reality. In this view, consciousness and quantum collapse are separate mysteries that happen to coincide without causally connecting. Others suggest that consciousness might be a quantum phenomenon itself, emerging from coherent quantum processes in neural microtubules or other biological structures. If minds operate quantum mechanically, then the boundary between observer and observed dissolves entirely. Consciousness becomes part of the quantum system it's trying to measure, creating recursive loops where awareness observes itself, observing reality. The question remains unanswered, leaving us suspended between equally troubling possibilities. Either consciousness has supernatural powers over physical reality, or consciousness is an elaborate illusion created by unconscious quantum processes. The mystery deepens as we contemplate whether our awareness creates the universe, or whether the universe creates the illusion of awareness within us. The quantum world vanishes the moment it touches the classical world. But nobody truly understands why reality chooses to hide its fundamental strangeness from everyday experience. Decoherence was supposed to solve the measurement problem by explaining how quantum superpositions naturally evolve into classical definiteness. When a quantum system interacts with its environment, air molecules, photons, electromagnetic fields, these interactions entangle the system with countless particles. The resulting entanglement spreads quantum information across so many degrees of freedom that superposition becomes effectively invisible. Think about this like trying to keep a secret in a room full of people. The more people who overhear fragments of your secret, the harder it becomes to maintain coherent secrecy. Eventually, so many people know pieces of the information that the secret loses its private character entirely, becoming public knowledge through environmental exposure. In the quantum realm, interactions with the environment serve as uncontrolled measurements that destroy superposition without conscious observation. An electron spin becomes entangled with nearby atoms, which become entangled with photons, which become entangled with detector circuits. The quantum information spreads outward like ripples in a pond until it's diluted across macroscopic systems too complex to track. This explains why we don't see quantum effects in everyday life. Your coffee mug doesn't exist in superposition because it's constantly interacting with air molecules, photons, and gravitational fields that entangle it with the environment. The quantum coherence that would allow macroscopic superposition gets destroyed before it can manifest at human scales. But decoherence doesn't actually solve the measurement problem. It just pushes the mystery deeper. The mathematics shows that environmental interactions create entanglement between systems and surroundings. But they don't explain why this entanglement produces definite measurement outcomes, rather than larger superpositions that include the environment. If a quantum particle becomes entangled with a detector, which becomes entangled with a computer, which becomes entangled with a human observer, why doesn't the entire chain exist in superposition? Decoherence explains why superposition becomes practically unobservable, but not why it becomes actually non-existent. The process also raises questions about where the boundary between quantum and classical behavior lies. The transition appears continuous rather than discrete, suggesting that the classical world emerges gradually from quantum foundations without any sharp dividing line. Scientists have demonstrated that decoherence rates depend on environmental conditions. Isolated systems at extremely low temperatures can maintain quantum coherence for extended periods, while room temperature systems lose coherence almost instantaneously. This suggests that the classical world isn't fundamental, but rather emerges from quantum systems through environmental interaction. Recent experiments have achieved quantum effects in increasingly large objects by carefully controlling their environments. Scientists have created superposition states in molecules containing hundreds of atoms, mechanical oscillators visible to the naked eye, and even small diamonds levitated in vacuum chambers. Each success pushes the boundary between quantum and classical behavior further into the macroscopic world. But the mystery remains. Why does reality seem to prefer classical definiteness over quantum superposition? Why do environmental interactions destroy coherence rather than creating larger, coherent systems? What determines the scale at which quantum strangeness fades into classical normality? Decoherence explains how the quantum world hides from classical observation, but it doesn't explain why it chooses to hide at all. Quantum mechanics contains a principle so absolute it transforms the entire history of the universe into an indestructible record. Information cannot be destroyed, ever. At the quantum level, every process is fundamentally reversible. Wave functions that spread can theoretically be refocused. Entangled systems can be disentangled. This time reversibility requires that no information about a system's initial state ever truly disappears. Think of it like a cosmic library where books can be rearranged, scrambled, or written in different languages. but every word that ever existed must remain somewhere in the collection. You might scatter pages across millions of volumes, encrypt the text in unbreakable codes, or hide sentences in the spaces between other words. But the information itself becomes immortal. The principle seems innocent enough until you consider its implications. Every thought you've ever had, every decision you've made, every quantum measurement you've observed gets encoded as information in the universe's wave function. This information cannot disappear. It can only be scrambled, distributed, or transformed into forms that become practically impossible to retrieve. When you burn a book, the information doesn't vanish. It gets encoded in the precise arrangement of ash particles, the exact spectrum of light emitted during combustion, the thermal vibrations of air molecules heated by the fire. In principle, a sufficiently advanced intelligence could analyze the smoke, ash, and heat to reconstruct every word on every page. The information survives in scrambled form. But information conservation becomes truly unsettling when applied to consciousness itself. If your thoughts are information patterns in your brain's quantum state, then every mental experience becomes permanently inscribed in the universe's memory. Your embarrassing moments, your secret fears, your private thoughts, all of it survives forever in the quantum information structure of reality. The principle creates paradoxes when applied to black holes. Black holes seem to swallow information permanently, creating an apparent violation of quantum mechanics. The event horizon acts like a one-way membrane that prevents information from escaping. Yet Hawking radiation emerges from black holes in forms that appear to carry no information about what fell inside. Some physicists propose that black holes don't actually destroy information, but instead encode it on their surfaces or in their radiation in ways too subtle for current technology to detect. Others suggest that information falling into black holes gets quantum teleported out through radiation, maintaining conservation while making retrieval practically impossible. The most disturbing possibility is that information conservation applies retroactively to the entire history of the universe. Every quantum event that ever occurred, from the Big Bang to the formation of galaxies to the evolution of life, remains encoded somewhere in the current quantum state of reality. The universe might be a vast information storage system that preserves perfect records of everything that has ever happened. If information truly cannot die, then nothing you experience ever completely disappears. Every moment of consciousness becomes a permanent addition to the universe's infinite memory, suggesting that existence itself might be fundamentally about information processing and storage. Black holes devour information and seemingly destroy it forever, creating a paradox that threatens to tear apart the logical foundations of quantum mechanics and general relativity simultaneously. When matter falls into a black hole, it carries information. The precise quantum states of every particle, the exact arrangement of atoms, the complete specifications needed to reconstruct whatever disappeared beyond the event horizon. Classical general relativity suggests this information vanishes permanently once it crosses into the black hole's interior, lost forever to the outside universe. But Stephen Hawking discovered that black holes aren't perfectly black. They emit thermal radiation due to quantum effects near the event horizon, slowly evaporating over astronomical timescales. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely, but smaller black holes disappear much faster. Here's where the paradox becomes terrifying. Hawking radiation appears to be perfectly thermal, random energy with no information content whatsoever. If you throw a library into a black hole and wait for it to evaporate, the emerging radiation shows no trace of the books that fell inside. The information that described every word on every page seems to have been destroyed completely. Think about this like feeding documents into a fire that produces only random heat and light, with no way to reconstruct the original text from the thermal output. Except this fire is gravity itself, and the documents represent the fundamental quantum information that defines the structure of reality. Information destruction violates quantum mechanics at the deepest level. The theory requires that information be conserved, that the complete quantum state of any system can theoretically be reconstructed from its future evolution. If black holes permanently erase information, then quantum mechanics fails catastrophically for any system that contains or interacts with a black hole. The paradox forced physicists to choose between general relativity and quantum mechanics. Either information gets destroyed in black holes, violating quantum theory, or it somehow escapes through Hawking radiation, violating our understanding of event horizons and thermal radiation. Recent theoretical work suggests that information might be preserved in black holes, but encoded in ways so subtle that it appears to be lost. Some proposals involve information storage on the black hole's surface, where quantum effects create holographic records of everything that falls inside. Others suggest that Hawking radiation carries information through quantum correlations too complex for current mathematics to decode. The most radical solutions propose that black holes don't actually have interiors in the way we imagine. That matter falling toward the event horizon gets frozen in time from the outside perspective and eventually gets returned to the universe through quantum processes we don't yet understand. In this view, black holes are information storage devices rather than information destroyers. But the paradox remains unresolved despite decades of brilliant theoretical work. Either quantum mechanics is incomplete, general relativity is wrong about black hole interiors, or information conservation fails in extreme gravitational environments. Each possibility threatens fundamental assumptions about how reality operates. The random thermal glow emanating from black holes might contain perfect quantum memories of everything that ever crossed the event horizon, encoded in correlations so subtle they transcend current human understanding. Hawking's original calculation treated the radiation emerging from black holes as perfectly thermal, random energy with no information content, like heat radiating from a generic furnace. This thermal nature created the information paradox, suggesting that quantum records of infalling matter disappeared permanently when black holes evaporated. But recent theoretical breakthroughs suggest that Hawking radiation is not truly thermal. Quantum effects near the event horizon create correlations between outgoing radiation particles that encode precise information about everything the black hole ever consumed. These correlations are incredibly subtle, virtually indistinguishable from thermal noise, but they preserve complete quantum records nonetheless. Think about this like a library that appears to be destroyed in a fire, where the exact pattern of sparks, smoke, and an ash carries encoded information about every book that burned. The encoding is so complex and distributed that it looks like random debris, but a sufficiently sophisticated analysis could reconstruct every word from the apparently meaningless thermal output. The encoding mechanism involves quantum entanglement between particles falling into the black hole and particles that eventually emerge as Hawking radiation. As matter crosses the event horizon, its quantum information becomes entangled with the black hole's internal structure. This information then gets gradually transferred to the outgoing radiation through quantum correlations that span the entire evaporation process. The information doesn't emerge immediately. A photon that evaporates from a black hole today might carry quantum memories of matter that fell in millions of years ago. The entire thermal output must be analyzed as a single quantum system extending across astronomical timescales to decode the hidden information. Scientists have calculated that retrieving information from Hawking radiation would require collecting virtually every photon the black hole ever emits and performing quantum measurements of impossible precision. The amount of computational power needed to decode these memories exceeds anything conceivable with current technology, making the information practically irretrievable, even though it's theoretically preserved. But the existence of this hidden information resolves the black hole information paradox. Quantum mechanics and general relativity can coexist because information is never actually destroyed, only encoded in forms so complex that extraction becomes virtually impossible. The universe maintains its logical consistency at the cost of making some information functionally inaccessible. The implications extend beyond black holes to information processing in general. If quantum correlations can preserve information in apparently random thermal radiation, then information might be hidden in many systems we consider informationally dead. The thermal noise in electronic circuits, the random motion of gas molecules, even the cosmic microwave background radiation might contain encoded quantum memories of their histories. Some physicists propose that the entire universe operates as an information processing system, where apparent randomness conceals deeper patterns of quantum correlation. Every thermal system might be performing computations we can't detect, storing and processing information through mechanisms that transcend classical understanding. The fundamental equations of physics work equally well forward and backward through time. Yet the universe displays a clear arrow of time that breaks this symmetry in ways that suggest reality itself might be fundamentally lopsided. At the microscopic level, physical laws show perfect time symmetry. If you filmed an interaction between individual particles and played the movie backward, the reversed sequence would obey exactly the same physical principles as the original. Particles scattering in reverse look identical to particles scattering forward in time. Quantum wave functions evolving backward follow the same Schrödinger equation that governs forward evolution. But macroscopic reality violates this symmetry completely. Eggs don't unbreak. Smoke doesn't flow back into cigarettes. Memories don't predict the past. The statistical mechanics of large systems creates an emergent arrow of time that points from ordered pasts toward disordered futures, even though the underlying physics treats both directions as equivalent. This asymmetry becomes disturbing when applied to quantum mechanics. If the fundamental laws are time-symmetric, then quantum measurements should work equally well for predicting the future and retrodicting the past. A quantum measurement today should provide just as much information about past quantum states as it provides about future ones. Think about this like watching a movie where the plot makes perfect sense played in either direction. But somehow the characters only remember events from one temporal direction while remaining completely ignorant about events in the other. The story itself is symmetric, but the characters' experiences break that symmetry artificially. Recent experiments have demonstrated quantum retrodiction, the ability to use quantum measurements to infer information about past quantum states. These experiments show that quantum mechanics genuinely works backward through time with the same precision it works forward. The mathematics treats past and future as interchangeable, even though macroscopic experience suggests they're fundamentally different. But time symmetry breaking in quantum mechanics might not emerge from statistical mechanics alone. Some interpretations suggest that quantum measurement itself creates temporal asymmetry by collapsing wave functions in ways that privilege future over past. If measurement determines reality rather than just revealing pre-existing properties, then the act of observation might literally create the arrow of time. The most unsettling possibility is that time symmetry breaking emerges from consciousness itself. If conscious observers play a special role in quantum measurements, then awareness might be the phenomenon that distinguishes past from future. Before consciousness evolved, the universe might have been temporally symmetric, with quantum events flowing equally easily in both temporal directions. Cosmological considerations add another layer of mystery. The universe began in an extremely low entropy state immediately after the Big Bang, creating the thermodynamic arrow of time that points from order toward disorder. But why the universe started in such a special configuration remains completely unexplained. The initial conditions seem fine-tuned to create temporal asymmetry in ways that appear designed rather than natural. Some physicists propose that our universe is just one half of a larger, time-symmetric cosmology, where entropy increases in both temporal directions from some central minimum. In this view, there might be another half of reality, where time flows backward from our perspective, populated by conscious observers who experience the opposite temporal direction as forward. Quantum mechanics might allow genuine backward-in-time influences, where future measurements reach into the past to determine the very causes that led to those measurements, creating closed loops of causation that violate every assumption about temporal order. The possibility of retrocausality emerges from the time-symmetric nature of quantum mechanics combined with certain interpretations of quantum measurement. If wave functions can evolve backward through time as easily as forward, and if measurements can select specific quantum states from superpositions, then future measurements might genuinely influence past quantum events. Consider a quantum delayed choice experiment stretched across astronomical distances. A photon from a distant galaxy passes a massive star acting as a gravitational lens, creating two possible paths toward Earth. The photon's path choice, determined by our measurement setup, doesn't just reveal which route it took. It actually determines which route it took during its billion-year journey through space. But retrocausality extends beyond delayed choice experiments to more fundamental questions about quantum measurement. If the collapse of wave functions is real, rather than merely apparent, then the measurement process might genuinely reach backward to select which quantum states were always true, creating genuine influences that flow from future to past. Think about this like playing chess against someone who can move their pieces backward through time to counter your strategies. Except instead of chess pieces, we're talking about the quantum events that determine the structure of reality itself. And instead of a game, we're talking about the causal network that defines existence. Some interpretations of quantum mechanics explicitly embrace retrocausality. The two-state vector formalism describes quantum systems using both past and future boundary conditions, allowing future measurements to influence past quantum states through backward-evolving wave functions. In this view, quantum systems are genuinely influenced by their entire space-time history, including events that haven't happened yet. From a classical perspective, the mathematical formalism handles retrocausality without logical contradictions by ensuring that no information can be transmitted faster than light. Future influences on past events are always balanced by past influences on future events in ways that preserve the consistency of space-time. You can't use quantum retrocausality to send messages to your past self because the quantum correlations only become visible after both measurements are complete. But this limitation doesn't eliminate the disturbing implications. If future measurements genuinely influence past quantum events, then the history of the universe remains partially unwritten until quantum measurements fix it retroactively. The Big Bang, stellar nucleosynthesis, planetary formation, and biological evolution might all depend partially on quantum measurements being performed in the distant future. Recent experiments have tested retrocausal interpretations by looking for correlations between quantum measurements and past quantum states that exceed what forward causality alone could explain. Some results suggest weak retrocausal influences, though the evidence remains controversial and alternative explanations haven't been definitively ruled out. The most unsettling possibility is that consciousness itself operates through retrocausal quantum effects. If awareness involves quantum measurements in neural systems, then conscious experience might genuinely reach backward through time to influence the brain states that create consciousness. Free will could be real, because conscious decisions retroactively influence the quantum processes that led to those decisions. In the deepest laboratories studying quantum mechanics, particles have been observed doing something that defies the very concept of causation, arriving at their destinations before they finished leaving their starting points. Quantum tunneling normally describes how particles can pass through energy barriers that classical physics says should be impenetrable. An electron can tunnel through a wall by temporarily violating energy conservation, borrowing energy from quantum fluctuations and paying it back so quickly that the violation becomes undetectable. This process allows impossible things like radioactive decay and the nuclear fusion that powers stars. But recent experiments have revealed something far more disturbing. When particles tunnel through barriers, the process appears to take negative time. Particles emerge from the barrier before they finished entering it, creating a temporal paradox that suggests quantum mechanics allows backward time travel at the microscopic level. Scientists measure tunneling time by analyzing how long particles spend inside the barrier region. Classical physics predicts that particles should spend time traveling through the barrier at some finite speed. But quantum measurements consistently show that the transit time is not just zero, it's negative. Particles somehow complete their journey through the barrier before they fully commit to starting it. Think about this like watching someone exit a building through the back door at exactly the moment they were still entering through the front. The person completes their journey before finishing their departure, violating every assumption about how sequential events should unfold in time. The negative tunneling times aren't just measurement artifacts or mathematical curiosities. Multiple laboratories have confirmed the effect using different experimental techniques and various types of particles. Photons, electrons, and atoms all display negative transit times when tunneling through appropriately designed barriers. But the mechanism behind temporal tunneling remains completely mysterious. Some physicists propose that quantum uncertainty in energy allows particles to briefly violate energy conservation and travel faster than light through the barrier region. Others suggest that the particle's wave function peaks emerge from the barrier before the main wave packet enters, creating an apparent faster-than-light group velocity. The implications extend to consciousness and free will. If neural quantum processes involve temporal tunneling, then thoughts might influence their own causes, creating mental experiences that partially determine the brain states that generate them. Decision-making could involve consciousness tunneling backward through time to influence the quantum processes that lead to conscious choices. But temporal tunneling raises profound questions about the nature of causation itself. If effects can precede their causes at the quantum level, then the logical structure of physical law might be fundamentally different from classical expectations. If consciousness causes quantum wave function collapse, and consciousness itself emerges from quantum processes in the brain, then reality faces an infinite regress that can only be resolved by some ultimate observer whose nature transcends the quantum systems it observes. The measurement problem creates a chain of quantum dependencies that extends without obvious termination. A particle's quantum state collapses when observed by a detector. The detector's state collapses when observed by a computer. The computer's state collapses when observed by a scientist. But the scientist's brain consists of quantum systems that should also require observation to become definite. This leads to an uncomfortable question. Who observes the observer? If conscious brains are quantum systems that exist in superposition until measured, then consciousness itself needs an external observer to collapse it into definite experiential states. But this external observer would also be a quantum system requiring its own observer, creating an infinite chain with no foundation. Think about this like an infinite tower of security cameras, where each camera monitors the one below it. But every camera needs to be watched by the camera above it to become definite. The tower extends infinitely upward, with no ultimate monitoring system to ground the entire structure in concrete reality. Some physicists propose that the ultimate observer must exist outside the quantum mechanical description of reality. A classical measuring apparatus that interacts with quantum systems but doesn't follow quantum rules itself. But this creates an arbitrary boundary between classical and quantum domains, with no physical justification for why such a boundary should exist. Religious and philosophical interpretations suggest that consciousness might be non-physical, operating outside the quantum systems it observes. In this view, awareness transcends material reality and genuinely causes wave function collapse through some non-physical mechanism. But this requires consciousness to have supernatural powers over physical systems, violating the causal closure of physics. The many worlds interpretation offers a different resolution by eliminating wave function collapse entirely. In this view, there is no ultimate observer because no observation actually causes collapse. Instead, conscious observers split into parallel branches, experiencing different measurement outcomes, creating the appearance of collapse without requiring external observation. But even many worlds raises questions about the ultimate nature of the universal wave function. If every quantum system exists in superposition across parallel branches, then what determines how these branches evolve? The Schrödinger equation describes wave function evolution. But what governs the equation itself? At some level, there must be mathematical laws or logical principles that transcend the quantum systems they govern. Some physicists propose that information processing, rather than consciousness, serves as the ultimate observer. In this view, any interaction that reduces quantum uncertainty counts as measurement, eliminating the need for conscious observers. But information processing still requires physical systems that should themselves follow quantum rules. The most disturbing possibility is that there is no ultimate observer, that reality consists of quantum systems observing each other in closed loops with no external foundation. The universe might be a self-referential system that creates its own meaning through circular dependencies between consciousness and quantum mechanics. Or perhaps we are the ultimate observer, collectively creating reality through our shared conscious experience of quantum systems that exist only because we observe them. Observing each other, the regress continues indefinitely. Seeking an observer whose existence could ground the entire hierarchy of quantum measurements in some form of absolute reality. The most frightening prospect in quantum mechanics isn't that these paradoxes are unsolvable. It's that they might all have simple, elegant solutions that reveal reality to be far stranger and more disturbing than even the paradoxes themselves suggest. Every quantum mystery we've explored points toward the same unsettling conclusion. The universe as we experience it might be an elaborate illusion created by conscious observation of deeper realities that operate according to principles we can barely imagine. Wave-particle duality, superposition, entanglement, measurement collapse, and all the other quantum paradoxes might be surface phenomena hiding something far more profound. Consider what a complete solution to quantum mechanics might look like. If consciousness genuinely creates reality through observation, then the material universe becomes secondary to awareness itself. Physical laws, particles, and forces would all be elaborate constructions created by minds that somehow exist prior to the reality they observe. We wouldn't be biological entities that evolved in a physical universe. We would be conscious beings dreaming the illusion of materiality. Alternatively, if this many worlds interpretation is correct, then our entire experienced reality represents just one infinitely thin thread in an infinite tapestry of parallel worlds. Every possible version of history exists simultaneously, including versions where physics works differently, where consciousness never evolved, where the universe never existed at all. Our sense of inhabiting a unique and special reality would be revealed as the deepest possible delusion. Think about this like discovering that everything you think you know is just one story in an infinite library where every conceivable story is equally real. Your life, your thoughts, your entire universe would be nothing more than one book among infinite volumes, no more significant than any random arrangement of words and possibilities. If quantum mechanics points toward digital physics, then reality might be computational rather than material. We could be information patterns running on some cosmic computer, experiencing the illusion of physical existence while actually consisting of nothing but data structures and algorithms. Death wouldn't mean the cessation of consciousness, but merely the termination of one computational process among countless others. The most terrifying possibility is that solving quantum paradoxes reveals existence itself to be far more fragile than we imagine. If reality depends on conscious observation, then the universe might cease to exist if consciousness ever stopped observing it. If wave functions require measurement to become definite, then unmeasured regions of space-time might exist in permanent superposition, neither real nor unreal, until awareness finally encounters them. Perhaps the real horror is that these paradoxes serve as protective mysteries, shielding us from truths too devastating for human minds to accept. The confusion and uncertainty might be the universe's way of preventing conscious beings from discovering the ultimate nature of existence until they're psychologically prepared for revelations that would otherwise drive them insane. Scientists continue their investigations, driven by curiosity that might be leading toward discoveries that fundamentally alter human understanding of existence, consciousness, and reality itself. Each answered question reveals 10 new mysteries, as if the universe actively resists complete comprehension. The final paradox might be that quantum mechanics can never be fully solved, because the solution would require conscious observers to transcend consciousness itself, stepping outside their own awareness to observe the very systems that create awareness. We stand at the threshold of ultimate understanding, terrified to cross. In the deepest laboratories on Earth, scientists have uncovered something that breaks every rule of reality we thought we understood. Particles that seem to remember the future, information flowing backward through time, objects existing in multiple places at once until someone dares to look. These aren't science fiction fantasies. They're quantum paradoxes that have left brilliant minds